Hello everyone, welcome back to another video, and today I will be explaining the Hardy-Weinberg equilibrium. What is the Hardy-Weinberg equilibrium? The Hardy-Weinberg equilibrium principle describes an ideal population that is not evolving. Think of it as a no evolution mode of a population. If nothing is changing in the gene pool, the allele frequency stays the same forever. In other words, the core idea is, if nobody messes with the population, the genetics stay frozen, like putting evolution on pause. There are three genotype frequencies. P squared represents homozygous dominant and can also be represented by two capital A's. The second one is 2p squared, which represents heterozygous frequency and can also be represented by a capital A and a lowercase a. And the last one is q squared, which is homozygous dominant. Q squared represents homozygous recessive and can also be represented by two lowercase a's. There are two equations. P plus Q is equal to 1, and P squared plus 2PQ plus Q squared is equal to 1. A population is only in Hardy-Weinberg equilibrium if there are no mutations, no natural selection, no gene flow, or aka immigration or emigration, random mating, or large population to avoid genetic drift. And you guys might be wondering, the Hardy-Weinberg equilibrium second equation, which is the P squared plus 2PQ plus Q squared, isn't that a bit similar to the quadratic equation? Well, yes, that's true. And I can prove it. So P squared plus Q squared multiplied by each other gives us a product of P times Q squared. And on the bottom you write 2PQ. This is all the X method, which you multiply A and C on top and you put B on the bottom. And now the goal is just to find two factors that multiply to give us a product, the product on the top, to give us a product on the top. And when the two factors add together, they give us the sum which is on the bottom. So it's pretty obvious that if you put PQ and PQ on both sides, this is right, because PQ times PQ is just PQ squared, and PQ plus PQ is 2PQ. And once you get the factors, you can rewrite it as P squared plus PQ plus PQ plus Q squared. It's all equal to 1. You can factor out a P here, so you get P plus Q plus Q, P plus Q. So according to algebra fundamentals, you have to eliminate one of these duplicate parentheses. So now you get P plus Q squared because you have one here and another pair here. So since that is duplicated, P plus Q squared is equal to 1. And if you decide to square root both sides, you get the original equation, which is P plus Q is equal to 1. So here's an example for the Hardy-Weinberg equilibrium. In a population of frogs, 9% of individuals have a recessive trait of green eyes, which is caused by genotype Q squared. Using the Hardy-Weinberg equilibrium, calculate the recessive allele frequency represented by Q, the dominant allele frequency represented by P, and frequencies for each genotype, which are P squared, 2PQ, and Q squared. So what is already given to us? So the thing that is given to us is q squared is equal to 0.09. And keep in mind, when calculating things in the Hardy-Weinberg equilibrium stuff, remember to convert percentages like I did, like 0.9 is equal to 0.09. Let's get right back to this. Q squared is equal to 0.09. And to get Q, you square root both sides. Well, I know what you're thinking. You might be thinking Q is equal to plus or minus 0.3. But the thing is that Q can only equal to positive 0.3, not negative 0.3, because it's not possible for allele frequencies or like probability things to be negative. Like think of like spinning a wheel or like roulette. There's no way you're gonna have a negative 25% chance of winning a prize, right? It's definitely positive 25%. So once you get Q is equal to 0.3, find your p-value, and to do that, pull out the definition or the equation. P plus Q is equal to 1. And when I plug in Q, it's P plus 0.3 is equal to 1. Subtract 0.3 from both sides, and you get P is equal to 0.7. After that, you may calculate the homozygous dominant frequency, which can be represented by PQ, if you recall it. So, as I just said, P squared is equal to the homozygous dominant allele frequency. So what I'm going to do here is find my p-value, which is right here. So 0.7 squared is equal to 0.49. And now, after all of this, the final thing you're going to do is to calculate the heterozygous allele frequency. The heterozygous allele frequency is represented by 2pq. And when you plug in your p and q value, you get 2 times 0.7 times 0.3. Now, 0.7 times 0.3 is equal to 0.21. And when you multiply that by 2, that gives us 0.42. And we're pretty much done. After this is done, You now have your final answers. Genotype and frequency.